record this. And then you've got two PDFs for today here, and this would be on the Canvas page. So that kind of procedurally gets us there. I would say, obviously, very unique times that we're sort of working through. And so again, if there's anything I can do to kind of help you guys at all, sort of online or offline, feel free to reach out to me. I mean, it's sort of goes without saying, these are unprecedented times. I mean, if we were together in a classroom, this would be the time to have a kind of a discussion like that, and talk about some of these, just really important issues that are out there. So I may not mention, but I went to Cal Poly, actually played football, played for two head coaches, and the second one was the first black head coach, actually, the history of Cal Poly, Andre Patterson. And then got a chance to come back here and teach, and I was a football coach here for 5 years. So I have a kind of a unique perspective on that. Obviously, that athletics and the football team is a location where the university brings in a portion of the diversity to the school and opens up opportunities for people to do that. And it's just really just a sad sign of events that is occurring, and hopefully there will be change that's positive and lasting and necessary. But I hope you guys are all safe with where you guys are, wherever you are. And I don't know if it's good news or bad news, but it's like, what next? I mean, it's only June. What else can 2020 bring? I know some of you are graduating, some of you aren't. I think most of you are, but so we do obviously have class on Thursday, so I'm not saying goodbye, but anyways, that would, what unique times that we're all facing. So I hope everything is going as well as it can. I think everybody is excited for this quarter to mercifully end. So anyways, if anybody does want to say anything at all right now, you feel free. And let's kind of wait a second here while I share a screen. I'll keep my eye on. I think we've got all the participants. So there's one more. All right. All right, let's do this. Let's get to the content for today. I guess my general point on all that was, in the midst of all this, foundations and excavation seem not as important, but we will move forward and expose you guys a little bit to this, and then we'll have a little bit of a little bit with tall buildings on Thursday, and then kind of a wrap up as well to the course. So let's see if, like cladding, foundations and excavation, this is going to be just a little bit of a exposure for you. We'll have a little bit of calculation on the other end of it. We didn't really have any calculations with cladding, more so just details that we were looking at. And again, we'll find a way to kind of encapsulate that a little bit for you. Make sure for For this, I'm going to expose you to just general issues, some particulars, and then, like I said, at the end, I'll kind of have two examples that'll have a little bit of calculation to them. So, um, we talked about this, and so I have a background, obviously, in engineering, and like, this is, where the loads from the building actually, get to the ground. And this is, literally like where the rubber meets the road. It's actually the ground that supplies, the equal and opposite reaction. If you think of the building as a whole, and the foundation. So the loads that end up at the bottom of the structure then have to transfer through the foundation, and that's basically what that foundation does. It distributes it widens the loads to a larger footprint. And the reason is because we're going to find out with a little bit of what the soil strength is and the stiffness is. So that's what we're working with there. Ultimately we need the ground to be the Newton's law, the opposite reactions, Newton's second law. So you can see the second one there. Buildings, have interaction to each other. That's why we put seismic separation to make sure those buildings don't hit each other. But even its neighbor, buildings would not be that close that they would be touching. But wind, has an effect with its neighbor. And just like foundations do also, buildings aren't just sitting alone in an open field sort of area. Sometimes they are, not all the time. And so then the local soil conditions need to be understood. This is where a geotechnical engineer generally is employed. Somebody who's going to do a soils report. That soils report then goes to the engineer. And again, the engineer is making decisions based on the foundation. So you're going to get exposed to just some of those decisions and some of the issues that go into actually building the necessary foundation. And one, it would just be access to the site and the ability of, mostly for machinery, if there is a need for large machinery, and certain foundations would have that need, which we'll get into. And then, a good foundation is, it's really not seen. It's kind of the most unglorious part of the building. You definitely don't walk in and probably appreciate the foundation of a building, but it's definitely heard when it's called upon. And when it's called upon, we definitely want that foundation to perform properly. And then those are, the issues are with gravity load, with lateral load. Again, those lateral loads obviously can be transferred in the vertical direction. And then also just the stability of the structure. So I'm going to go this is, I will just be completely upfront, just gratuitous, sort of pure shock value. This picture over here, I mean, kind of all of them. I mean, this is not these are not a pier here that is meant to be at an angle. But this picture over here, this very famous sort of picture of liquefaction. I believe this is in Japan. I should know that. But you would see here the building having a little bit of a soil issue. So like that building right there, it looks like it was actually pretty well designed. I mean, it's still intact. Definitely not very usable. And it's, again, I shouldn't make light of that, but you say kind of a very famous picture. And so I'll give you a second here, just kind of lead this, but I put this in, just takes me back to my kind of earthquake engineering roots. I studied that at Caltech for several years. So earthquake damage and liquefaction. Again, as an architect, you wouldn't, this deals with, a loss of strength and stiffness, as you kind of see there, generally from earthquakes. It's, characteristic of certain types of soil, and then, deals with water. So you see here, this is actually near water. But there could be a water table that could be close. And so it doesn't just mean that it's sort of down by the bay, although that is back historically, that is a place where silty soils exist. And that's why there were so many problems in the '89 Loma Prieta earthquake up in the Bay Area. That's how that a lot of that land was created. So very, stunning sort of pictures. Really nothing to really do a whole lot with what we were talking about today, but just sort of shock value, I guess. So from a construction point of view, excavation, site shoring, these are the topics that we'll be going over today. We'll look a little bit at retaining walls. We'll go very lightly with subsurface water. It's actually quite a interesting topic, but we're not going to spend really much on that. And then we'll do a little bit here. This will be with the calculation at the end, a little bit with some of the foundations, sort of a little bit more just typical foundations, some column foundation, and then a caisson or a drilled pier. So often with projects, especially large scale ones, there's an issue with excavating, either foundationally to get down to bedrock, or because the building is going to be, sort of have a subterranean component to it, and that excavation, could be on a slope. Just kind of think if you were to not dig on a slope here, then you would basically be creating a cliff, and that cliff would have instability. So the sloped excavation might be used. It's going to be a little tough if you have another building right next to the site. So this would be a picture over here where you've got a building that's, again, sort of in the middle of nowhere. So you're able to excavate at an angle. If not, then vertical shored excavation could be used, and we'll go over what this sort of temporary site shoring would be called, and this would be something that's engineered, which then gives for really kind of stunning pictures. So some of the excavation process. So these temporary site shorings would be, kind of read these 5 that we're going to look at, get you exposed to some vocabulary. And so that last one that we saw, or that first one, quite a vertical wall here. Not all are going to be that drastic or large. And so it's the soldier beam and lagging. So where that soldier beam is, really, it's a driven pile down into the soil, and then as you excavate, and then they're able to fill in with lagging, it's called. So you got drilled shafts for the soldier beams. So those are I-beams, and then they're spaced. One second. Spaced at such amount so that you've got wood lagging that's going to be put in there, that then would be shoring the site. The lagging is placed if depending on the height and just how much, you end up with lateral pressure from this earth. That earth really wants to move in this direction. It wants to fall this way. And the further down you go, the more pressure is present out there. So it's kind of analogous to, the deeper you go in a pool and how it hurts your ears. So you end up with more pressure down here. And so sometimes you may need a little bit more assistance just from the bow that could occur. And so you may end up with tiebacks that need to be inserted. And then that portion then becomes backfilled behind it. So that's the way this is done, is these are then going to be sort of vertical by themselves, quickly filled in with the lagging, and then backfilled on the other side. So here's sort of a smaller one. And like I said, we saw kind of a medium-sized one. And then depending on the height of it, you might need tiebacks. So another one would be a soil nail wall. And so those tiebacks in the other picture were less frequent. You obviously don't see any up here. You see a row of them here. So I mean, they're spaced, and then they're relatively close to each other. But from a vertical distribution as well, they're not as closely spaced as a soil nail wall. And so this excavation occurs in layers, about 5 feet at a time. So here you're just seeing at the very end of it, after they've excavated the entire thing. So they're going to start up here a row at a time. And as they go, then install, right, you kind of read that here, the soil nails in each of those, right, kind of 5 to 6 feet in each direction. So you kind of think of the 5 by 5 spacing, and then apply a thin layer of shotcrete with each layer of excavation. So it's kind of like nailed, but you see the frequency of those. So they're very different than a tieback. And again, there is a limit to exactly how high those can go. And so you're really dealing a little bit more with just the construction issues with which one might be used, either the soldier beam or a soil nail wall. Sheet piling can also be used, and just like it's going to go straight down, right? It's going to be driven down in. So there's a drive effect to this thing. It doesn't just sink down in; it has to be pushed down in, but with repeated blows at the top. So we'll get to that also in another one a little bit later with driven piles. But sheet piling can also be used as a water barrier. The way it interlocks, it's going to use the soil pressure to its advantage in that regard. And then it can be cantilevered, or it could also be tied back, depending on the height of it. Gets higher and higher, then you would need to put tiebacks in. Again, really more of it's a stability issue. And then the excavation can occur on one side. Once it's been installed, then you excavate on one side of it, clearly. So a slurry wall, kind of some neat pictures here. It almost looks futuristic of sorts here. And so this slurry wall, kind of read about it here. This is what's going to be used, generally when we need, when we are restricted with space. For one, if you're dealing, like here you kind of see a downtown type of high-rise area. So again, it's excavating while simultaneously placing slurry to replace the earth. So this is a clamshell-shaped digger. And so it's going to dig, and then there's going to be tubes that then take that out while it simultaneously puts, the slurry in. And then once that's all done, then place the concrete from the bottom of the trench, displacing the slurry. So that slurry is kind of like this temporary holder of sorts. The concrete is what ultimately is going to go down there to be our wall. So you see the width of that thing right there. Another one would be a hydromill trench cutter. So you see those wheels down there. And so literally it just works its way straight down. It's going to be straight down. So it kind of digs a trench. And that trench is what the slurry simultaneously goes into. And then that's what keeps that trench from falling in on itself. And then excavating one side, and then you can install those tiebacks as you excavate. So that would be a slurry wall. Here would be some cross-lot bracing. Kind of get a look, and generally you could see multiple types on a job site, but here would be one definitely down in a downtown area with high buildings around, urban settings, deep excavations where tiebacks are not permitted. It could not be permitted because there's some sort of neighbor issue going on, and you can't get anywhere close to their foundation. So you'd have to build something on your without tiebacks that reach all the way back. And so then just in general here, some retaining walls. I'm gonna do this. I'm gonna go about just this slide and then take a quick little break here. Um, so from these different types of retaining walls. So here's a couple of different shapes, and it really actually brings forward all the issues that kind of surround them. So you've got a change in elevation. So if you can put a wall between the two, right? One's just going to hold back the other. Clearly, this can have a stability issue. This is going to want to push. This thing's going to want to push this way. This is being held, so it's like going to want to tumble. And again, this just has to do with the aspect ratio and how it's designed. So that can all be overcome by design. Another way to do it is to create an L-shaped, to where this push is also being resisted by this push. So the sort of L shape is going to work for your stability. So just like anything, it would be depth to width. A little bit also with water involved. Here would be another type of retaining wall that would have a foundation down here that would spread out. You kind of see some rebar that's dashed in there, and that rebar would always be on the tension side. So is this getting pushed this way? The back face here would be in tension, and this would be wanting to be pulled up. So this back face here would also be in tension. So dealing with unequal soil levels, and then also this might be a wall in a building. If there weren't soil here, you could end up with a retaining wall being part of your building. So here would be another construction piece. And you see lines here. This is called what would be called a cold joint. So these would be poured or constructed in two different pieces. So same thing here. So that would have to have reinforcement across it. And to help with the sliding, because as this push here, not only does it want to tumble, but it also would want to slide horizontally. So this is called a key. And that key allows for more bearing pressure, because as this thing wants to slide, and it would be bearing against those two faces right there. So that's what that key, called a shear key. And so that would help with the design or the sliding stability of the retaining wall. So let's do this. I'm going to take about a 4-minute break here in just a moment. All right, I'm back. Thank you. I don't know what it is, but my shoulder keeps getting tight when I do this. Um, Perhaps I never really thought I'd be doing this. If you notice my light, though, I got one of these babies now. Yeah. So, anyways, if I look a little brighter, that would be why. So, okay. As my computer starts to run, I think the other thing that's going to happen as this quarter comes to an end, I have a feeling my computer is going to walk off into the sunset as well. Boy, that little feller likes to run. Oh man, poor guy. So just a little bit more with tieback sites. So you saw that picture earlier of that the tiebacks that have been inserted, and kind of just give you some scale here with the type of machinery that's necessary. You know, again, depending on the tiebacks are not the nails, the soil nails, but you know they are much less frequent, so more load is to them. So I give you a little bit of a picture of what these things look like. So I'm going to go a little bit bigger here on the picture. I mean, I guess you've got this as well if you want to, but so yeah, I didn't need to go that big clearly. So there's a little bit of a look at this thing as to where the drilling, and then a little bit of a section as to where the bonding goes, the grout which is injected, and then the jack, and then there's a plate and an anchor head. And so that's what gives, right? Getting all the way back away from the wall. And then this is the amount of bonded length. So this is done to get far enough into the soil. We need to, get deep into the soil so that there's not a local, failure of the soil. So that's why this wouldn't just be right here, because that whole load gets distributed out into the soil. It's sort of the general theme of the of the uh, foundation process. But here, same thing with these tiebacks. So give you a look at that. So that's why that would be something that would be, generally pretty expensive due to the machinery, and that's why we had brought up that issue about access to the site as well. So I'm just going to go quickly on this with water. And it could be a water table issue, which is present, even if you can't see it. And then sort of the idea of the local and then the global, so that you can have localized failures or water, global failures in water. And so the kind of the issue comes down to then the expansion and contraction of the soil. So when the water leaves, the soil then contracts. As it's there, then there's expansion. And so, the other side of that is, if there is, there's soil expansion that actually sort of pushes on your building, and that would be what's called hydrostatic uplift. So not a huge amount to kind of worry about there, but an issue nonetheless. So, all right, kind of getting into the home stretch here. So we're going to go with a little bit with foundations. There'll be a little bit of calculations on the back end of this. So this is the piece that we'll do. There'll be a little bit of this on homework 4. There'll be something that deals with a foundation calculation. So this is where those loads are transferred to the soil. They could be in multiple directions. Primary failure is going to be settlement. It's going to be the when we say settlement, it would be the structure settling on the soil. So obviously I shouldn't say obviously. This is why with high-rise buildings, those are drilled on foundations that go all the way down generally to bedrock, so that there is less of a settlement issue with the weight of the building settling on the soil. This is where a geotechnical engineer would give the values. So there'll be a allowable bearing pressure that we'll talk about, and then also an allowable friction, so shear stress, and two types, shallow and deep, right there. So we'll kind of go through both of them. Um, so this would be footings. You kind of see with a column slash wall footing, it could be combined, very much most common. And so you kind of see here, the pad, right? The footing underneath the column, which will be eventually to it. Now these are, that's rebar that is going to be, that's permanent, that's been cast with the foundation. And so there'll be a cold joint there, and then you'll have more rebar that'll go to the column above. And to do this, we need adequate soil bearing pressure. So this really just sits. Now it's embedded in there. It's not stopped right there, but at the very bottom, it's just sitting. It's sitting on some soil. As you kind of see here, where something would be poured, and then it would be then filled again. So this is not going to be for something substantial, but from a size. And so we're talking about the pad here. The area is going to be the load divided by the allowable bearing pressure. So the pressure is going to be like in pounds per square foot or kips per square foot. That load, that's the load in the vertical direction that we would know is being delivered from the structure. Gravity and seismic, depending on if it were part of the lateral system. So, and again, there can be a combination. So here are just some very small construction. Right, a mat foundation be a little bit different. This would be one that is a continuous thick slab, and it's often called like a raft, a raft foundation. I mean, literally, the building is sitting, on this entire slab. Could be some post tensioning involved, some sort of, depending on the size of it. But it's used for soils with low bearing pressure generally, and just allowing for the load to be distributed to the entire soil. So unlike on the picture above here, that column load is going to come right down into that pad. Now, nothing's going to be footing wise, at least, going to be counted on out here. There's going to be footing that's going, or a slab that's going to be there, but that slab won't be asked to carry much load. So this would, in a situation like this, if you had weak soil, so the cost of this is that, between, the between the columns, like it's a continuous span. So that all has to be continuous and it's going to act in a monolithic fashion. So it'd be efficient for, something that had columns that were closely spaced. It would be efficient for it. Often can be used on large construction projects like hospitals. Deep foundations, and so those first couple, those were all shallow foundations. Little excavation needed. Deep foundations, drilled piers, caissons, driven piles. Generally, these would be higher cost, but used to get to the bedrock when necessary, but also just to help with increasing surface area for settlement and uplift. So we'll talk about the two ways that these are generally designed. So kind of take a look take a look at all of these here. So a drilled pier, exactly what it sounds like. That's a huge drill that is turning, right? Going to go straight down. So it's straight or belled drilled shaft is what these would be used for. They're going to be filled with concrete reinforcement steel cage. Casing might be needed to prevent the soil from caving in on itself. Now, it would highlight this word relatively quiet. I mean, you think that would probably make a little bit of noise, but compared to the driven piles, that's why we would say relatively quiet. And two ways that the analysis would occur here, if it's based on friction, right, and friction that would be on the edge, right, on the surface of the foundational pier. So the length is going to be equal to the load divided by the allowable friction times the diameter. I think I have that wrong. Give me 1 second here. Actually, let me hold off on that. Hold on. So I've got that wrong, actually. That would be the circumference. Sorry. So that would be the circumference. And you'll see that. We'll do an example on that. Sorry, got that wrong. No, can't do it. Design may be based on end bearing. So at the very bottom of this thing, right, there would be just like a shallow foundation. You'd have a load divided by the allowable bearing pressure, and that would give you the necessary area at the bottom of that drilled pier. So that would be something that if it were to be all the way down on bedrock and you couldn't account for any of the friction. So it just depends on really what the pier is being used for. If there's no bedrock down there, then you would not be really accounting for the edges of it. If there were soil down there, then you could be using for the end bearing. We'll do an example where we actually check both of those, use one or the other. Driven pile foundations. This looks like a lot of fun. We would end up with driven piles. We've got a kind of an end result picture here. And so literally that is just going to pick up a weight and smash it down. And it's just going to drive continuously down into the ground. And so this is why on that previous, when we said relatively quiet, this would definitely not be quiet in any sort of fashion. And so these could be, precast concrete. It could be steel that's being driven. Obviously, if it's being hit, the length. There's a stability issue with the, with the concrete or the steel, such that it doesn't buckle. So it could be, in the end, it could be based on end bearing or on friction. And allowable load is set by the geotechnical engineer and confirmed by the construction crew. Actually, they'd be able to tell with, how far with each hit. It becomes a physics problem, an impulse momentum type of problem for any engineers out there. I think Allison might have a little bit of a mechanical background, so I do know that that would be a ME212 problem right there. So so that would be the driven pile foundations. So let me see if this will flip. All right, let's do this. We got two examples. Give me a thumbs up. Do you see did it change for you guys? Give me a thumbs up, a clap, a coffee. There we go. Got one, got two. Actually, I shouldn't say that. I'm not looking at all of you. So, or your names. There's a lot. So, oh, that was the other thing as I was thinking about the beginning of class, like I know we said that before, but like I'll always sort of know you by well, for most of you, like by your picture here. If you've got a picture with your Zoom persona, um, or just your name. But anyways, all right. All right, so a column footing here. And so I'm going to just get down to the bottom down here. That's the picture we're talking about. So we've got a column, right? And this is like that one picture you had seen earlier. So there's the footing. And so the load from the column, and then a slab would be poured afterwards. So the focus here would be that column and then this footing. And so this whole thing would need to be detailed with proper reinforcement such that the load could work its way, right? It could work its way all the way out to the corners. It could radiate out. So there's some detailing that's involved there to make sure that it does and that the shear is properly accounted for. But down here, that bottom, that's now where this load, which is coming down, now is going to be resisted down here on the very bottom of this footing. So you see how there's more surface area down there on the bottom. So that's what we're about to sort of go through a calculation on. So given an allowable, kind of let you read that. The geotechnical engineer get a soils report, and you're told that the bearing pressure, allowable bearing pressure. Now the allowable, this actually also incorporates a factor of safety. So it doesn't mean that if we were at 5.1 kips per square foot, that we would have a failure, like our soil would not be able to bear. That's just the allowable, generally that uses a factor of safety. So it's quite multiples more of that before we would start to get into a failure type of area. So just keep that in mind here. That's a allowable, sort of a working value. That's not the ultimate value. So let the column force be, let's just say, 250 kips. So just basic design principle, right? The calculated, right? The design value needs to be less than or equal to the allowable value. So the calculated, what we calculate in our structure, right? This is the allowable stress design. So normal stress, P over A. So this is a load from the column. Could be a factored load, like we would have, and divided by the area, and that's the bottom, the area at the bottom of the footing, and that would need to be less than or equal to 5 KSI. And so a very simple kind of math, area will come up here. So the area needs to be greater than or equal to a little bit of math. And so this is kips divided by feet squared. So we end up with 50 feet squared. And if we've got a square pad, so where it's L squared, so area would just be L squared, so L needs to be greater than or equal to square root of 50 if we use the square pad. So on that, you could say, well, but 7 times 7 is 49. And so you would be able to, with the fact that it's so close to 5 KSI and the factor of safety would be in there. It would not be like, well, let's just use 4 feet by 4 feet. I mean, obviously 49 is very close to 50. It's off by about 2%. So anyways, just keep that in mind. You could say 8 by 8 or 7.5 by 7.5 as well. You could do that same thing as well. So, all right. And then the last one here would be a drilled pier. So I'm going to give you the picture of it here on the right. And so this would be a drilled pier of some length L, right? That drilled pier has some diameter and some length, all right? And let's kind of take a look here. You're given from the geotechnical that given two values, the shear stress, let's say the allowable shear stress, it deals with the friction. It's going to be 1 KSF, kips per square foot. The allowable normal stress, let's say, right, 20 KSF. And again, we have drilled deeper, one way to get to better soil. And let's just go back and say that we've got that same 250 kip force from the column coming down. Again, we've got one reason why you have to do this because we've got such bad soil up top that we need to get down to better soil. So it's going to be done two ways. One would be, hey, we've got, we know that we need to go down some length L to get to this 20 KSF kips per square foot, allowable normal stress. So bearing stress. And so we need to do that, and we're going to need a certain diameter of our drilled pier to be able to do that. So we got P over A again. There's a force from the column divided by the A. That's the area of the very bottom down here. So we're going to end up using pi r squared in just a second. And just this is the calculated, needs to be less than the allowable. Right? And so we've got to do a little bit of math. So I just kind of flipped it, inverted, and kept A over there. So A needs to be greater than 12.5 square feet. And then to find the radius, I'm going to use pi r squared. A little bit of math gets me to about 2 feet for the radius. So I end up with about a 4-foot diameter. So that'd be one way to design this. We would end up with a 4-foot diameter, but caveat is we would need to be able to go all the way down to, right, whatever L was necessary to get to that soil. So another way to do it was if we were given, right, we were given the shear stress or the friction that is allowed for the drilled pier. Sorry. And so it's also called skin friction. So we're going to need to use all this area here. Right? That all, if you think of this thing pushing down, right? The soil is pushing up against it. And we're going to assume that it's constant. It actually wouldn't be constant in real life. It would be some distribution, but then we would get into integrating, which I don't think we really want to do. So this one, we would say we're going to use a 3-foot diameter, and we would say that we're going to use a 3-foot because of the stability issue. So this would kind of need to be told to you. We're not doing a stability analysis here, but we've got now the shear stress, it should be the shear force, right, divided by the A, where A now is the surface area. So this is not P over A. Right? Now we're into the shear stress. So this would be shear force, right, which is the same as the column force. It's just now the force that's being transmitted, right, across the, or on the edge of the pier. And then A, right, A would be the surface area on the side of that pier. And so that surface area is going to be L times the circumference. So this is what I had incorrect earlier. I had diameter there. And the, so it's L times the circumference, which would be 2 pi r or pi times d. And so then that's how we're going to end up, right, using our information about the diameter. And so that diameter is going to fit in there. And so all we've done is our math. And if we were to do it this way, we would need a 27-foot long drilled pier. So that would be how we would end up designing these two. So again, a drilled pier, right? Bearing pressure or friction. And then here would be a column footing, a shallow footing, and that would just be bearing pressure right down on the bottom there. So, all right, so I finished a little bit early. So let's just kind of get on the same page here. So this content would end up showing up just a little bit on homework 4. That would be that one that's going to be on next Monday, right? You've got project 3 that's going to be due Monday. I need to go to Canvas and change that due date. You can certainly turn it in before then. That would be just fine. Oh yeah, that was the other thing. As I was thinking, boy, that sun. There you go. Let's see if I can turn that. So as I was saying about you guys, I'll know you guys from your Zoom back. You'll probably know me from like, he was sitting in front of that funny window covering for the whole quarter. Anyways, and so I think that'll kind of get us there. I would be happy. I will be here until 6. I'm going to take about. I'm going to take a 8-minute break. So I'll be back at 5:15. It's completely fine. Let me turn this off.